Hello everyone, I'm Arjun Singhvi and I'm pleased to present a paper on CliqueMap, a distributed caching and serving system at Google. This paper is a collaboration between the authors listed on the slide and between Google and UW-Madison. Our paper describes the system itself and also some valuable production challenges and experiences which we hope will be of use to the broader community. To summarize our work in a single slide, in-memory serving and caching systems are critical components in hyperscale data centers. They are used throughout the industry, at Google and elsewhere. In the previous few years, we deployed and evolved a distributed remote memory access and RPC hybrid system in Google's data centers called CliqueMap. In composing RMA and RPC technologies and then putting them into production for a variety of Google services, we encountered and addressed productionization challenges which we summarize here and in the paper. In broad terms, these challenges arise from how to navigate trade-offs. For example, how to deliver high availability and low cost, how to achieve efficient use of both CPU and memory, how to evolve the system over time, how to interoperate with established systems written in a variety of high-level languages, and how to deal with data centers that are non-uniform in their hardware capabilities. We'll outline our approaches to these challenges in this talk. Our paper has more discussion. To give a brief overview of the system, CliqueMap is a hybrid RMA-RPC serving system that builds around the core idea of using two simple RMA reads in sequence to perform a lookup operation. We call this protocol 2x-R, and it is shown as a sequence diagram on the right. In a 2x-R lookup, the first read is from a distributed hash table which forms an index over all the stored key value pairs. The hash table entry contains a pointer to the location of the actual data itself. A self-verifying checksum ties the two reads together to detect race conditions. As the system has evolved, the logical idea of two reads in sequence still holds, but we've deployed optimizations to cut this down to a single round trip time in some cases. In the 3+ years it's been in production, CliqueMap has grown beyond a petabyte of DRAM capacity and more than 150 million global QPS. The critical feature of the system is that it uses efficient RMAs for the critical part of lookups and RPCs for all other operations. These include mutations and cache fills, which tend to be less performance critical than cache lookups. They also benefit significantly from the high programming abstraction of RPCs, which we demonstrate later in the talk. While RPCs are the default choice for communication in distributed systems, RMAs has been gaining traction. The key difference between these primitives is that RMAs are essentially fixed function and don't invoke application code at the target. In contrast, RPCs are fully programmer defined at the target. At Google, feature-rich RPCs offer significant advantages but lag behind RMA operations for outright efficiency. To design a system embracing only one of these key primitives is a false dichotomy. Systems can leverage the strength of RMAs and RPCs in concert, complementing one another. With CliqueMap, we opted for a design in which lookups are performed by RMAs, but RPCs also play a substantial role, including all cache mutating operations such as set or add. We embraced a design in which these two technologies can compose gracefully. To realize this goal of composition and yet also be resilient to the production challenges we outline, CliqueMap builds on the idea of a distributed hash table, which are generally friendly to remote memory access. CliqueMap augments the hash table with checksums covering keys, values, and metadata. Clients performing lookups verify these checksums end-to-end, and in doing so ensure that RMAs can see a consistent view of the underlying data structure even as it is mutated by concurrent RPCs. Taking advantage of self-verification, our design then adds retries, specifically retries at a level of the stack that makes sense for a particular error. For example, simple checksum failures are attributed to races against RPCs and are retried simply by issuing fresh RMA reads, assuming such a race will not recur. In contrast, inconsistencies in metadata are retried at a higher level, for instance after refreshing configuration state from external storage. The principle behind self-verification and retry is to give implementation freedom to the server-side RPC logic. Ultimately, that logic needs to be concerned about making retriable conditions transient, detectable, and rare, easier to achieve than making these conditions impossible or invisible. This brings us to our production challenges. For each, we will present the challenge, how a system building on RMA might be particularly challenged, and also CliqueMap's approach to the challenge. Our first challenge is how to navigate the space of availability and cost trade-offs in a distributed system. RPCs are powerful in this context since they often come with useful features for fault tolerance like deadlines and cancellation, which aren't present in RMA primitives. Like many systems, CliqueMap offers replication in order to tolerate individual failures in the system. The R is equal to 3.2 mode in particular provides a means to form a quorum, a majority vote among three possible replicas. An upside of this design is that a slow or failed replica can be tolerated so long as the other two are responsive and in mutual agreement. As we evolved the system, we later augmented this capability with the introduction of quorum repairs and warm spares to further bolster availability. Our second production challenge lies in delivering a cost-effective system, which means delivering a product that efficiently uses both CPU and DRAM. Choosing RMA as a primitive is largely motivated by CPU efficiency, but actually threatens memory efficiency if deployed naively. Making a memory range RMA accessible requires memory registration, a fairly slow process that needs to be done off the critical path, enough so that it's tempting to just pre-allocate large memory ranges in advance. But this approach essentially over-provisions DRAM and risks stranding it. Despite this, we did launch CliqueMap initially with over-provisioned RAM, but later deployed features to dynamically reshape the backend memory footprints. This change took advantage of the self-verification and retry approach outlined earlier, since clients could lazily discover the change in the configuration whenever a lookup would fail benignly. Specifically, it enabled backends to change the size of the memory they advertise to the clients in a recoverable way. The initial rollout saved a substantial fraction of RAM. The plot shows one CliqueMap customer's change in RAM footprint. Of note, scaling the backend size dynamically intrinsically ties RAM usage to demand, so that less human interaction is needed in the sizing and operation of the cell, making it easier to deliver on both CPU and memory efficiency expectations. We offer some more technical details on this in the paper. A third challenge to highlight is the need to simply maintain a system over time and further help it to evolve throughout its useful life. While RPC infrastructures can make it relatively easy to change protocols over time, RMAs directly expose in-memory object formats between clients and servers. These clients and servers are built from different sources at different times and roll out at different schedules, so changing the underlying format is not straightforward. Here again, CliqueMap relies on its self-verification properties, which allow addition and removal of fields from binary objects. This generic approach has proven highly versatile, enabling over 100 protocol changes, large and small, to CliqueMap over time, including the introduction of an entirely new primitive like scan and read shown in the graph here on the side. When operating atop Pony Express, a software NIC at Google, CliqueMap can use a special inbuilt primitive to flatten the canonical 2x-R lookup into a single round trip, essentially a highly specialized RMA operation embedded in Pony Express. Introducing scan and read happened during CliqueMap's production lifecycle and was significantly simplified by a disciplined approach to protocol versioning. Challenge 4 is language interoperability, which is made more challenging by RMA in that RMA's most prevalent libraries offer C language family bindings, which threatens to root RMA-based systems with C++ clients only. While some languages offer native execution options, such as JNI in Java, this approach adds still another level of complexity to the design. Despite these difficulties, tens of thousands of software developers at Google operate day-to-day outside the C++ language families. Furthermore, established infrastructure uses RPCs to bridge programming language gaps. A critical serving system might be written in C++, but its support pipelines must leverage other languages, and both will have a need to access a distributed storage system. CliqueMap's initial inability to target non-C++ clients made it a non-option for early customer engagements. To correct this strategic shortfall while also keeping complexity under control, we now deploy the normal CliqueMap C++ client in a sub-process alongside non-C++ clients. We use IPC mechanisms to route operations and data in and out of the sub-process. Named pipes for Go and Python, and we have also deployed a shared memory solution for the Java client. The graphs on the right plot the CPU efficiency and op latency that results from a sub-process approach. While some of the outright efficiency advantages degrade, CliqueMap is accessible from a variety of languages and at full speed and efficiency from C++. A final challenge we highlight is the practical need to operate across a variety of non-homogeneous hardware deployments. Not all servers, NICs, or networks are the same, simply because data centers age and aren't built all at once. Despite this, it's desirable to present near uniform capability, regardless of the age of the underlying clusters, and so we have invested in specializations for CliqueMap's protocols to the underlying networks, making it capable of operating on a variety of networking gear. Our paper details how we scale the performance of CliqueMap cells differently on different hardware-software platforms and take advantage of programmable NICs such as Google's Pony Express to build support for CliqueMap's lookups directly into the underlying infrastructure. Our 2x-R protocol itself was amenable to deployment on one RMA, a non-programmable but performance all-hardware RMA solution. By helping to abstract away some of the details of the underlying hardware, CliqueMap makes high-performance distributed storage accessible to large groups of potential collaborators and internal customers. This concludes the first portion of our talk. In the second half, we'll discuss some behaviors of the R is equal to 3.2 quoruming features in detail, including races and failure tolerance. To begin our deeper look at R is equal to 3.2 and quoruming, consider the hash table layout we saw previously. Each key value pair is represented by an entry in the index region and an entry in the data region, together covered by an end-to-end checksum. When a client has successfully copied both to client memory, it can verify the checksum and the metadata. When the checksum comparison succeeds, with high probability the blocks are not corrupted, for example by a concurrent mutation. When the formats and the metadata match the client stored configuration, the client can also be assured it is consistently interpreting the underlying data. With these basic capabilities in mind, we will now offer a closer look at a race condition in R is equal to 3.2 to illustrate some of these mechanisms in action. Here we have pictured a sequence diagram depicting the protocol actions of a client C1 that will try to set the value of key K to value V1. Meanwhile, a second client C2 tries to look up key K. Initially, all the three backend replicas, S1 through S3, have an established quorum of key K at value V0. We will walk through some possible interleavings of these operations that show how our rules work around self-verification. Bear in mind, these operations are mutually unordered. In general, they race to arrive at each backend. The interleavings we show are just examples meant to illustrate how the protocol works to ensure consistency. The RMAs comprising the bucket fetch operations are simple and fairly responsive. They return to client C2 information about the metadata for key K, read from each backend's index region. Once two such responses have been received, it is possible for C2 to form a metadata quorum, that is, to determine that key K has value V0, although the value itself has not been fetched yet. The third bucket fetch, yet to arrive, is not relevant to this finding when the first two respondents agree on V0, as is shown in this example. Meanwhile, the RPC's underlying C1 set operations require CPU scheduling at the destination, and the actual moment of update might be prone to delays. These and other sources of delay mean that the replicas will apply their updates to key k, in this case changing its value from v0 to v1 in an uncoordinated manner. Once at least two of the replicas have applied the update, an objective observer can note that the quorum changes from v0 to v1, which we highlight in light blue. In our running example, we have intentionally shown a case in which the fetching client C2 sees key k's metadata before an update, but observes the datum from after the update. As the example progresses, we will see this will lead to a self-verification failure at C2 and eventually trigger a retry. Lastly, note that the RPCs underlying a set send responses to C1. C1 can declare its own set to be complete once it observes two of the three of these successful responses. The third one can even be lost without affecting the correctness of the operation. We conclude our example with the data fetch from C2. C2 can begin fetching the data. However, the datum itself has been overwritten, but the client has not yet detected the change. The client issues another RMA to fetch the data from S3 in this case, as it was the first to respond to the bucket fetch. This operation returns a full data entry, which includes key, value, formatting information, other metadata, and checksum. Critically, this checksum was computed based on both the index metadata and the data entry itself. But before declaring a success, C2 verifies that the checksum holds end-to-end. And in this case, it does not. C2 has read the index entries before they were updated by the RPCs, but it has read the data entry after an update has occurred. At this time, C2 can declare its lookup attempt to have failed, but it can retry the lookup again, usually with an expectation of success. We have shown an example here in which a set can destructively interfere with a get's forward progress. And in fact, the overall lookup process in CliqueMap is obstruction-free. In practice, we find that the actual rate of competition is manageable. See our paper for more details. The upside of the replicated design is failure tolerance, which includes maintaining nominal performance even during adverse conditions. This figure plots the lookup latency percentiles, median in green and tail in orange, of a synthetic client as it probes up for random keys in a CliqueMap cell. While that load is running, we forcibly and abruptly restart one of the cell's backends, simulating a failure condition. This backend then restarts on another host, but loses all of its data. In blue, we plot the RPC byte rate among the backends, which increases significantly in the middle of the experiment. This corresponds to the repair traffic. Other backends are actively reinserting missing data in the restarted backend, quickly restoring a clean quorum. Of note is that amidst the failure and the repair, there's little change in the median or tail latency as observed by the clients. These clients tolerate the loss of the backend because not all three backends are needed to serve a get. By around 1425, the system has fully recovered. While the previous graph plotted behavior during an abrupt loss of a backend, most backend restarts are benign, a function of weekly binary upgrade cadence. In these cases, backend tasks have ample warning that they are about to shut down, and do so in a controlled sequence. For these cases, CliqueMap offers warm spares that can temporarily take over a backend's working set while it undergoes a restart. As with the previous example, here we are plotting lookup latencies in green and orange and overlaying inter-backend RPC byte rates in blue. This time, there are two significant spikes in the RPC traffic. The first one occurs when the target backend is shutting down, as it is voluntarily moving its data to a spare. The second spike occurs when the spare is returning the data to its newly restarted home node. As with the case of the unplanned failure, we see little or no change in the client observed performance during a maintenance event. The key advantage of sparing isn't that it has minimal performance difference, but rather that it maintains 3 copies of data throughout planned maintenance operations. Put another way, R is equal to 3.2 CliqueMap tolerates failures while undergoing maintenance at the same time. As we close the talk, I'll leave you with these remarks reflecting our overall experiences with CliqueMap and its productionization. We managed to build a system that combines the strengths of RPCs and RMAs and further managed to deploy it widely. In doing so, we developed means to evolve the system over time by embracing a protocol that could self-correct, in our case with checksums and retries. We then refined the system over time to address new requirements, support for non-C++ languages, more efficient management of RMA accessible memory, and deep cross-functional optimization with programmable NICs. We hope that future system designers will benefit from this discussion and look forward to systems that can take advantage of our advice. Thank you on behalf of the CliqueMap team.